Thank you very much to the committee for inviting me, and I'm honored to be here to present to you Engineering with Nature. Engineering with nature as it's being practiced within the United States. It's a newer concept in the U.S. and I just wanted to go through with you a little bit about how we see the engineering, basically the design of our infrastructure to complement instead of fight against natural forces to provide benefits to society. Okay, basically what we're doing in the United States, well, we've adopted engineering with nature because it's a good idea, and basically the status quo was becoming unsustainable. We could not get the economic benefits, the environmental benefits, and the social benefits out of our waterways and coastal areas that we needed in order to keep everybody happy, to maintain what everybody wanted from these regions. So the needs are efficient, cost-effective engineering and operational practices, more collaboration and cooperation, and less unproductive conflict, of which we had a lot in the United States between government groups, business groups, social groups, environmental groups. And when we have meetings, we discover that a lot of our interests actually do align. We just got to get a practice in place that will help them align, and that's where engineering with nature comes in. And we need sustainable projects which will win for all three of these groups. So what engineering with nature is, if I could just give it the definition as we have it written up for the Corp, is the intentional alignment of natural and engineering processes to efficiently and sustainably deliver economic, environmental, and social benefits through collaborative processes. Key ingredients include science and engineering. We don't want the engineering to fight natural processes, for example. We want it to complement them, whether it's the infilling of a channel, if we can design a channel such that it doesn't infill as bad, or design a port that doesn't so degrade the natural environment around it. Using the natural processes to maximum benefit to get these needed functions from our coastal and watersheds. Broaden the extent of benefits provided by the projects, and science-based collaborative processes to organize, focus, interest, stakeholders, and partners. And if you look at the figure on the left there, there's social interests, economic interests, and environmental interests, and there's a region where they overlap that we call sustainable development. Considering the engineering with nature opportunities, we have key factors, what we call the 4 Ps in English, because they do come into 4 words that begin with the letter P. It's the processes, the physics, the geology, and the biology, and what we call coastal engineering jiu-jitsu, which is trying to get them all to line up such that they complement instead of fighting each other. One force works with the other. Programmatic content, text, planning, engineering, construction, operating or regulating of our ports and coastal infrastructure. Project scale can be from an individual property owner up to a watershed in an entire region. And performance, configuring the system, then quantifying the benefits, then checking that we're getting the benefits out of the system that we need with our engineering with nature solution. We have something we call Engineering with Nature Pro Map. I'll give a website at the end of this. This is a GIS-based database of projects illustrating engineering with nature principles and practices. It currently contains over 200 projects, and it includes the reports and contact information for each of these projects. So that website will be given at the end. And it's designed to facilitate communication about opportunities, lessons learned, both good and bad, because we've had our share of failures, and I'll even discuss one of those, and provide links. And projects are being added continuously. Some examples of engineering with nature solutions: strategic placement of dredge material. We see dredge material as a benefit. It is a resource, not a byproduct of the dredging process that should be considered as something that has to be handled as a solid waste, unless that material is contaminated, in which case we do handle it as a solid waste. But otherwise, we are wasting a very good resource. The example on the left here is a receding shoreline of a barrier island right next to an entrance channel at Savannah, Georgia, and how dredged material that is not pure sand, not beach quality, can be used to develop berms to support shoreline stability and enhancement in that region, while minimizing rehandling the reintroduction of the sediment to the channel itself. The one on the right is coming out rather pale, but it is Mobile Bay. We took the material 30 miles, about 50 kilometers offshore to dispose of it, where it is a sediment-starved bay. It needed mud. Wetlands were receding. So we developed an engineer with nature solution to reintroduce the mud from the dredging process back into the bay. We're still working on how to optimally place the dredged material to benefit the wetlands and other resources that need the mud. But right now we are reintroducing the mud into the bay system. This is another example. I'm giving a few examples here, and then I'll go into how Engineer with Nature's kind of gotten on an accelerated course due to some of the big storms we've had in the U.S. in the past few years. This one is at Wilmington, North Carolina, where they were deepening and widening a channel, and they took the material from that channel and built that T-shaped structure to the right-hand side of the channel in a configuration and an orientation that should enhance biological activity, and it did. It's become a very popular sports fishing ground. It's not big enough to really become a commercial fishing ground, but they have competitions out there, and it is a popular feature, and as storms degrade it, it can be added to during the natural dredging process. Another example is a receding barrier island in Florida, in Tampa Bay, where they put these, what we call reef balls. They're structures that are designed to stabilize the shoreline, but instead of just being a solid structure that stabilizes the shoreline without providing any environmental benefit, they're specifically designed to enhance oyster habitation. And they're doing that. They're stabilizing the shoreline, creating new habitat, not just for oysters, but for other species as well. And this is one where we had a degraded bar on the Loosahatchee, and we wanted to restore the bar, so they reconfigured some of the flow such that during high river flows, it would go, enough water would get into the bar to restore the wetland and restore the habitat on the bar, but not enough to permit infilling of the channel. So it's working out rather well. They're getting new habitat on the bar that had disappeared from the bar. And another example of Engineer with Nature Solutions, for the sake of time and brevity, I'm just going to talk about the one is the Upper Mississippi River training structures. The chevrons there, they were specifically designed for two purposes. One is to funnel the flow into the channel to keep it clear. For shipping, the channel is on the left-hand side there, but also create quiescent areas of water that was beneficial to some habitat that used to live in wetlands and such that have been degraded by ship wake and other processes from our navigation activity on the river. And it's worked quite well. Habitat has been restored within the inner circle of the chevrons, and there are fish species that breed there and such. And another example is reconfiguring how we build breakwater blocks, such that they're either dimpled or they have shelves that are conducive to permitting habitat to grow and expand on those blocks, whereas they would normally be a void zone for most habitat. And here is one of our not so great examples. We spent $25 million to construct 650 acres of sandbar for the endangered least tern. It's a bird species that nest in sandbars. And this is in the upper Missouri River, one of our major waterways in the States. And then came along the flood of 2011 and created 16,000 acres for us, basically inundating the 650 acres that we had created and humbling everybody. But it's a natural process. Now we're monitoring that 16,000 acres to see if during the non-flood years it's being degraded. And if it is being degraded, is there a way we can stop that degradation? Oh, near, okay, sorry. We're doing a good bit of process research in this. I want to say it's not just all about looking at the big scope. We're looking at the smaller scope. We're looking at, for example, in the laboratory, we're developing wetlands to see how sediment can be transported through those wetlands during wave current environments. And one of the things we're noticing is that, yes, it reduces the orbital velocities, which is good for sedimentation, but it increases the turbulence, which is not as good for sedimentation in those environments. And next, we're going to take this same measurements out into the field by looking at, instead of looking at a degrading wetland, what we're looking at is an accreting wetland, see what we're doing that is right. This is where there is a diversion from the Mississippi River into what's called the Wax Lake River Delta, and the delta is accreting. We want these deltas to accrete to provide storm protection, to provide habitat, so they have both social and environmental benefits and economic benefits. And so we want to understand what's going on right, so we're monitoring it right now. And I'll go into that a little bit more in another presentation. But to understand these natural processes, we really have to get in there and measure them, both in the laboratory and the field. And then changing topics a little bit, we have something called the North Atlantic Coast Comprehensive Study of Natural and Nature-Based Features. What it is, as part of the Engineering with Nature initiative, we're trying to replace, well, first of all, we had what was called Superstorm Sandy or Hurricane Sandy, which hit the Northeast a few years ago and heavily damaged natural and man-made storm barriers. We've taken this as an opportunity for broad-scale application of engineering with nature restoration. Specific locations are being selected for engineering with nature analysis. And it's a systematic approach for evaluating natural and nature-based features, soft infrastructure as opposed to hard infrastructure, soft infrastructure that can provide all three benefits, economic, social, and environmental, to these systems. And we have a report out on this describing this integrated approach of developing natural and nature-based non-structural and structural measures, where they're needed, where you can apply these with some assurance that you will protect coastal areas. Many of these are in areas where there's navigation and such, so you don't only have to protect from the periodic large storms, you have to protect from the everyday ship passage and the bow wakes that are created by that, which can degrade shorelines. And the goal is to get a full range of environmental and social benefits besides the economic benefits that are required. These are some of the features: dunes and beaches, vegetated features, oysters and coral reefs. In the Northeast, there are no coral reefs, it's mostly oyster reefs, barrier islands, and maritime forests and shrub communities. And this is a list, and this is how it's broken down. This is just a subsample of some of them. There are more for inland waterways and such, and looking at the performance factors and the types of structure that could be built under this category. And then there's an implementation framework where you identify and organize the stakeholders and partners, which is critical. You find if you get all the groups to the table, the environmental groups, the social groups, the community groups, the government groups, the industries, the port authorities, you discover you have a lot more in common than you do when you're just dealing through regulation, where the regulation says you must do this, and it costs $25 million to build 650 acres, where nature will build it for free periodically. that type of thing. And then an iterative evaluation process where you define the physical and geomorphic setting, assess the vulnerability and resilience, and identify the natural and nature-based features that can protect against those vulnerabilities, and evaluate in up to 3 tiers depending on the need, and select a natural or nature-based feature if it's applicable, and then go back and iterate through that process. And then after implementation, how you monitor it, and after a big storm, how you evaluate its performance. The levels of, or the tiers of analysis could include just level 1, which is a qualitative characterization of performance, level 2, which is semi-quantitative characterization of performance, and level 3, which is a full quantitative characterization of performance. And there's multiple ways of doing this. I don't have the time to go into them. They're in that report. The link to that report is in the website that I'll give you at the end of the presentation. There's 72 individual performance metrics identified for natural and nature-based features. An example where we're applying this was a heavily damaged national wildlife refuge, heavily damaged by Superstorm Sandy or Hurricane Sandy. It's over 40,000 acres. The objective is to enhance resilience through engineering and restoration, and the means is by applying engineering with nature principles and practices to it. And we're collaborating with the U.S. Fish and Wildlife Service, which is a government entity tasked with protecting fish and wildlife, and the Endangered Species Act. Every year, the Corps spends $300 million U.S. to conform to the Endangered Species Act. By combining the Engineering Species Act with the authority within the Engineer with Nature, presents an opportunity to reduce the time and the cost and increase the benefits for species conservation. And we're finding that out in multiple examples where we're applying it. And as I mentioned, one of the critical things to do is to engage all the stakeholders early and often. And you'll find out that they'll say, yeah, go ahead, try that, and let's see how it works. Whereas if you just say, we're going to try this, the initial response is a no. Keep doing what you're doing. So we have been through a series of, as part of this Engineering with Nature implementation, through a series of meetings with multiple stakeholders, which includes industry and others. We've been working with a lot of environmental groups to see what their needs are and to see how Engineering with Nature can help support those needs. And some of those are the National Wildlife Federation, the Environmental Defense Fund, the Nature Conservancy, and the National Fish and Wildlife Foundation. And some reports have even come out of these and some workshops. And the dialogue sessions on Engineering with Nature included 22 internal USACE Army Corps stakeholders representing a diverse specialty of areas and geography, including senior leadership, research, navigation, flood risk management, regulatory, etc., and geographic areas around the U.S., both inland and coastal. And 34 external stakeholders representing a diverse population of organizations and regions, including academia, other government agencies tasked with environmental or economic priorities, state government agencies, local agencies, private industry, European experts, since the Building with Nature started before the Engineering with Nature, and diverse geographic areas again. And a lot of mental modeling went on here. What is just looking at what people perceive to be the barriers. And I love this plot because external is outside the core, internal is inside the core, internal is light green, external is dark green. What they perceived is barriers to Engineering with Nature adoption. Over 60% outside the core and over 70% inside the core said the core's culture is the problem. I think that's just kind of interesting, saying the organization that's trying to adopt Engineering with Nature is also seen as a problem. And it's a large organization, and I don't disagree with this. There is a lot of resistance to it. anyhow, these are the types of dialogues that went on to get to how we can implement engineering with nature practice and be able to bypass some of the very stringent regulations that are on the book, saying we are approaching them from a different angle, for example. And just as a final thought, this is the website. They're going to print out the slides, so you'll have this website and it'll have the report that I mentioned on it, as well as a lot of examples. And with that,